So the other day, while listening to the Modernize or Die podcast, I heard Brad Wood mention a algorithm that he created, or I should say a ColdBox module that he created to help detect memory leaks. And I was fascinated by this because it was so much more elegant than a similar solution that I came up with several years ago. So I wanted to dig into his approach a little bit more. So to demonstrate, I have two components. This one is thing1.cfc, and you can see it just stores some static data and has no additional logic. But as part of its initialization, it takes us thing2, so it has a nested component. Now thing2 is going to have a memory leak. If we jump over to thing2, you can see that it also has a bunch of static data of different types. But then as part of its initialization, it kicks off a CF thread, which will iterate and sleep 3 seconds and then store a new key into the variable scope. So this key that's being stored into the variable scope over time represents a memory leak that we want to be able to locate. And let's see how this comes together. So if we look in our application CFC, we can see that in the onApplication start lifecycle method, which helps initialize the application, I'm manually creating my thing1 component and I'm injecting my thing2 component. Remember, the thing2 component is the one that has the memory leak. And then as the very last thing that we do in our application initialization, we create an instance of our memory leak helper component and we pass in the application scope. Now, the memory leak helper, as part of its initialization, is going to start to recurse through this root container, which references our components, and then it's going to recurse down through the components. So it's going to look at thing1, it's going to see that it has thing2 internally, and it's going to start to track thing2 as well. And it's going to snapshot the state of the application, and then we can take subsequent snapshots at a later date and time, compare those to the original snapshots, and identify changes in the internal application state that may or may not represent memory leaks. So to see how this works, if we look at our index.cfm, which is going to be how we look at changes in state over time, what we can see is that we reach into the memory leak helper and we ask it to find memory leaks. What that's going to do is it's going to take a new snapshot of the application state, compare it to the old application state, and return the delta, which is what we are dumping out with the CF dump tag. It also has a get targets method, which just allows us to look at the list of components, the names of the components that are being tracked over time. Now you'll notice that I'm providing the top attribute here to the CF dump tag, and that's just so that we sort of limit the output of the dump initially, and then we can increase via the URL the depth of that dump as we see things that look suspicious. So let's jump over into the browser. Let me reset the application, and you'll see that initially here our our delta is empty because there is no difference between the initial application state and the current application state. And you can see that we've not only found thing1, which was right in the application scope, but we've also found thing2, which was nested inside of thing1. Now if we refresh the page, what you'll see is that the thread has had a chance to add a bunch of variables here to the scope, the internal private scope of thing2. And you'll see here that because we have the top default to 1, we don't get to see these local values. So if we dig deeper, you can see we pass top 2 in the URL. We can now see that those are structs, and again, we can dig deeper one more time to get the actual value. So what this allows us to do now is to see the changes in the application memory state over time, and we could identify here that we have a bunch of keys that are being used inside of methods, which are then being set into the variable scope, in this case accidentally, but potentially not accidentally for all cases, right? You just might have lazy initialization of values over time. But what this allows us to do is, let's just reset again, is be able to see the changes in state over time to help us identify changes in state that could be representative of memory leaks, right? All right, so now let's take a look at the memory leak helper to see how it works. So this is my translation of Brad Wood's original ColdBox module to work inside of an application, a really old ColdFusion application that doesn't have any framework whatsoever, doesn't have any dependency injection, basically works like this, where I do a bunch of manual initialization of components, and then I can actually initialize the memory leak helper and pass in the application scope. So when the memory leak helper initializes, it does two things. First, it gathers all the targets by recursing through that container, and then it gathers all of the initial snapshots. If we jump down to this, we can see that it uses sort of a pseudo-recursive algorithm. It stores this root container in this containers to explore. It then keeps popping containers off of that. It looks through the, let's see, it looks through the, first, sorry, let me think through this for a second. So for each container, it then looks at all the variables in that container. So initially when this gets called, it's going to be the application scope. On subsequent iterations of this while loop, it'll actually be the variable scope from a different component. So we can look to see if the key is null. If so, we skip it. We look to see if it's an object. Is object returns true for ColdFusion components and Java objects, so we know that if it's not an object, we can skip it. Is object, like I said, will return true for Java objects, but we're primarily interested in ColdFusion components, so what I do is I try to call get component metadata, which will fail for non-components. So if we have an error here, we can skip it because we know it wasn't a component. We can then check to see if it's already being tracked. If so, we can skip it. Otherwise, what you'll see is we get the variable scope for that target, and then we append that to the containers to explore, which we will then continue to pop scopes off of essentially to continue tracking. And then we return the initial target. So that gives us our initial set of ColdFusion components. And then once we have that set of targets, we can go ahead and gather all the snapshots. The snapshots, you can see we just map the targets onto snapshots, generating a snapshot for each. What that does is it gets the variable scope of the given component and then looks for keys that are not null, are not objects, and are not custom functions. And the reason that we're doing this is because we're trying to identify memory leaks. So the chances that, say, we have a custom, a ColdFusion component or a Java object show up that wasn't unexpected, or suddenly a new function to show up, those are much less likely to represent memory leaks. Though you couldn't rule it out. Again, you could always customize this code if you think that a ColdFusion component may represent a memory leak. To each their own. I also filter out some debugging properties that ColdFusion looks to, it looks like it creates when you do things like execute the CF query or CF lock tag. And then I simply map over those filtered in keys and I get the value identifier. This just essentially takes the value and creates a string representation of it that I can compare over time. So once we have our target and our snapshots, what we can do is find memory leaks over time. What that does is it takes the old snapshots, loops over them, maps over them, generates a new snapshot for the current target, and then calculates a delta between those two snapshots. And the delta essentially just compares the keys in the old snapshot and the keys in the new snapshot, and then where any of those key existence differences are or the key values differences are, it returns that in the delta. And that's the delta that we're seeing here. So it's essentially aggregating all of the keys that show up in the new scope that weren't in the old scope and then identifying those as belonging to thing 2. And I really like this approach. I think Brad's approach here is much more elegant than anything I came up with to try and solve the same problem. Again, this is my interpretation of his original ColdBox module. Your mileage may vary depending on your context. And yeah, I think I'm pretty pleased with this, and I'm using this currently to try and identify some odd memory usage in an application of ours. And yeah, definitely listen to the Modernize or Die podcast so you can pick up cool tips like this. And huge thanks to Brad for the inspiration.